Hi, in this video, we're going to take a look at neural networks for supervised learning. Neural networks are a super powerful tool for us to get like really powerful supervised learning models. They're pretty complicated. They're very black box, and they require a lot of work and they require a lot of data. So there's a lot of downsides to them, but when they deliver good. When you have a lot of data and you want the best model you can possibly get, neural networks is probably the best way to go. Neural networks handle a lot of like non-classical supervised learning problems very well, like things with like images and sounds and video, anything that's like non-standard data science stuff, like not a spreadsheet problem, you're probably going to be wanting to use a neural network. Almost surely. Now, my personal experience for spreadsheet problems, which has been like 90% of my career, neural networks are not the way to go. But they have a lot of power. They've got a lot of them. There's a lot of utility in them. So let's go ahead and start talking about them. All right, so first thing we want to do is I just want to go over this diagram. Now, this diagram I copied and pasted from creatively.com. Thank you, Creatively. Please check out their webpage. They did not pay me for this, for me to talk about them. I just copied and pasted their stuff, so I want you to know that that's where it's coming from. All right, so this diagram is the graph diagram of a neural network. Now, I didn't actually fit this model, didn't build it. This is just an image I copied. What's going on here is that we have 3 predictor variables. We have 2 target variables. Now, the target variables, if it's a classification, this could be like a binary classification where, such as like for heart disease yes, heart disease no. 2 different levels, which we would represent with 2 dummy variables. So here we have 2 target variables. Now, they don't have to necessarily be like dummy variables. It could be that I have, let's say, like humidity and temperature for a regression problem. All right, now, what's going on here is that think of these 3 predictor variables and follow the lines going to this light purple node. All right, we have 3 predictor variables going into here. What is happening is that in the structure of this, we have something that's very similar to a generalized linear model, where this purple is the target variable and these 3 are the predictor variables. And then, and so like this edge here indicates that we have a non-zero coefficient connecting within that generalized linear model. Now, when I get to this purple, the second purple one, these 3 are the predictor variables. And here, this is also for this purpose in this subgraph, this is also a generalized linear model. We have 3 predictor variables going into this as our target variable. This edge here indicates that there's a non-zero coefficient in the sub-generalized linear model. This indicates that there is a non-zero coefficient. This indicates that there's a non-zero coefficient also. And so you'll notice that how this works out is that when I go from left to right, every node on the left is a predictor variable for every target variable on the right. When I look at the blue and the purple, I've got 3 predictor variables. I've got 4 target variables. So I've got 4 in this blue to purple transition. I have 4 generalized linear models. All right, well, how many coefficients do I have all together? Well, I've got 1, 2, 3 coefficients plus the intercept. That's 4. I have 1, 2, 3 coefficients plus the intercept. That's 4. 1, 2, 3 coefficients plus the intercept. That's 4. 1, 2, 3 coefficients plus the intercept. That's 4. So just going from here to there, I have 16 parameters going on. Now, when we could take another step, when I go from this hidden layer to the output layer, once again, I have predictors, I have target variables, but now the hidden layer variables, these are my predictor variables, and the output layer, these are the target variables. And so when I look at this top purple, I can see that it has a coefficient going over to this target variable. The second purple has a coefficient going into the target variable. This has a coefficient going into the target variable. This has a coefficient going into the target variable. Okay, and so I can see that going from purple to yellow, I have two generalized linear models also. And well, how many coefficients do I have? 1, 2, 3, 4, plus the coefficient 5. How many coefficients do I have here, or parameters? 1, 2, 3, 4 coefficients plus the intercept 5. Okay, and that is a basic, the basic structure of a neural network is that every single hidden layer node is being treated as like an intermediate target variable. When I move from left to right, as I move from right to left, now that hidden layer node becomes a predictor variable for the layer to its right as we move on. Now, we can also have something called a skip layer. A skip layer is where, the skip is where like the input layer could have a coefficient going straight in over here. That's also a possibility. And we can have more predictor variables. We can have more intermediate hidden layer variables, and we can have more hidden layers also. We can have tons and tons, as many as we want. My experience for spreadsheet problems is typically one layer is good enough, and the square root of my number of predictors is about the right number of the number of nodes in the hidden layer. All right, so we can think of this as kind of like a tangled bag of generalized linear models. Now, technically, not every neural network aspect connects to a generalized linear model. ReLU is not invertible, that the function that used there in classic neural networks, so that doesn't have that connection. But if I'm using identity, hyperbolic tangent, or if I'm using logistic, which I'll show in a moment, those are all directly connected to a generalized linear model. In fact, if I was to go through, if I had predictor variables, nothing in my hidden layer and one output layer, if I use a hyperbolic tangent, identity, logistic, I actually have a generalized linear model right off the bat. And so there's also a vocabulary aspect. The activation function in neural networks is the inverse of the linkage function in generalized linear models. Weights in neural networks are coefficients in generalized linear models, and the bias in neural networks is the intercept in a generalized linear model. So there's a direct connection. And so a neural network is just a bunch of generalized linear models where we create like these we create the hidden layer variables to help improve the fit of our model. Now, with all these parameters, it's going to take more data to get a good, solid, reliable model. My personal rule is that I want 30 observations per parameter. Where did I come up with that? I didn't see that anywhere. I haven't read it anywhere. It's not from a blog post or a paper. I just go, you know what? In introductory statistics, I need 30 to converge to normal when I'm doing a t-test. You know what? I'm just going to use that as a criteria. If somebody comes up with a better one, please let me know. All right, so neural networks are super, super powerful if they're used at the right time, right situation, right use case. They have a lot of downside. Every single problem that comes up in supervised learning comes up in a big, big way with neural networks. These are so powerful and so flexible that if you have plenty of opportunity to do something stupid. And so we have to be mindful about this if we're going to go through this. Honestly, most of the time, I think they're not the best choice for my work. For the type of work that I've done, I've used them before in the past. I've been successful, but frequently for the amount of time and effort it takes to get a good model, I could have done something simpler like with stochastic gradient boosting or random forest. So if my data can be represented with a flat file, I'm going to lean away from using a neural network. But if I'm in a situation I've got, I'm doing something with images or sounds, if I have non-classic data, then I'm going to very much be looking to a neural network. All right, so neural networks, because they can pick up so many aspects of our data, they are prone to overfitting. And to protect us from overfitting, we need to have a lot of data. Also, neural networks really are the apex of black box models. It takes a lot of work to really figure out why something is the way it is because of all those hidden layers. If if my stakeholders say, well, why did the model say this on this case and not and said this on this other case? In my mind, these are very similar to each other. It's going to take me a long time to really figure out why that is. There are tools to help you out with that in Python, but honestly, just getting those to work, and I don't use them that often, so I'm not that proficient with them, is a lot of work in and of itself. Okay, neural networks suffer from every single problem that generalized linear models suffer from, and so that this means that we're going to need more data prep than other types of modeling that I could use. Also, very sensitive to outliers. Every single problem that is present in generalized linear models is present in neural networks. So outliers, gotta deal with it. There is a lot of things to work through. We have to do a lot of tuning. We have to figure out the number of layers. We have to figure out the number of nodes in each layer. We have to figure out what activation functions we're going to use. Am I going to use a skip layer? Am I going to use a bias? Am I going to use an epoch? Epoch is just running repeatedly. And to what extent? This is a lot of stuff to have to wade through. Now, if I've got the time and the money and the data to do all this, great. It will be very powerful, but frequently for me, I don't have that luxury. So honestly, for a spreadsheet problem, for the amount of work, they're usually not worth the effort compared to what I can get much quicker off of a tree-based model. Now, that being said, I got through my disclaimer, neural networks are super powerful when used in the right cases. They can handle situations. If I have a lot of data, I can absolutely handle or get a very, very good model with a neural network. Now, generally, I avoid using neural networks for spreadsheet problems, but spreadsheet problems is a good place to start. And we're going to use scikit-learn in this video. If I need a serious neural network, I'm not going to be using scikit-learn. I'm going to be using another package within Python. There's lots of tools within Python for this that will do a better job, but the parameters and the setup and just how things work in scikit-learn is very similar to everything else that we've been doing in this video. Everything else I do at work, it's a good place to start. All right, so now in my experience, overwhelmingly, I only need one hidden layer, and the square root of the number of predictors is all I need for my number of nodes in my hidden layer. I fussed around, fought with it. I worked on projects, and I have had improvements, but not really great improvements over that. Typically for spreadsheet problems, my experience alone, I just need one layer. Square root of the number of predictors is enough. All right, and so when I say weight in this, weight in a neural network is, think of that as the coefficient in a generalized linear model. In other supervised learning models, when we say weight, we say the amount of influence that an observation has on the overall model. Well, here weight means how much influence does a variable have in the model, and that particular sub generalized linear model. All right, so just to kind of show you how we can get a lot of parameters off of this. So here I'm just going to take a Keras model. I'm not going to fit it. I'm just using this computation to show what's happening. So let's say I have 784 predictor variables, definitely reasonable professionally. Let's say that my first layer, I have 32 nodes in the hidden layer, 64 in the second, and then 1 in the last. And you'll notice I've got ReLU, and then sigmoid as my activation functions. And so you'll notice that in the first, going from 784 to the 32, I've got 25,120 parameters going on. All right, that's going to be 32 times 784 plus all of the intercepts. And then going from the first hidden layer to the second hidden layer, I've got over 2,000 parameters going on. This is going to be 32 times 64, which is 248, plus the 64 biases, the intercepts, which is 2,112. And then you'll notice that when I go from the last hidden layer to the target variable, I've got 64 coefficients plus the bias plus the intercept, which is 65. All right, so the total number of parameters is over 27,000. Okay. So, if I want to build a model like this, I would really want to have 30 times that for the amount of data that I'm going to have. So I'm going to need, at least, 500,000, over, well and truly over that. All right. So generalized linear models have a direct connection to neural networks in that each of those sub models, when I go from left to right, all the nodes on the left are predictor variables, and each node on the right is a target variable. And so we're going to have a weighted sum of our variables, and then we're going to pass that into the activation function. The activation functions will be the activation function. If there's an inverse function to it, the inverse is going to be the linkage function of a generalized linear model. ReLU doesn't have an inverse. It's a very simple function, but I'm not going to really worry about that. Now the bias is the same as an intercept, and the weights are the same as coefficients. And so we have our input layer. These are the overt predictor variables. I have my output layer. This is my overt target variable. And then I have my hidden layers, which act as hidden covert predictor variables and target variables, depending on what the relationship is at that particular point in the graph. Right now for data preparation, neural networks suffer all the problems that generalized linear models have. And so I cannot have any missing values. Either I need to kick them out or I need to impute if I have missing values. We really, really, really do want to standardize our independent variables. Typically, I encounter a lot of students that want to put things on 0, 1, minimum 0, maximum to 1. That works great if I'm in a situation where I'm dealing with pictures, where I've got pixels, where I know that the maximum is 255 and the minimum is 0. That makes perfect sense. For my work, when we're doing something like money or height or temperature, my data set, what I have in my data probably isn't going to be the largest value that I'm going to see over the life of the model, over the project. And so typically, when we're dealing with data that doesn't have a hard fixed bound on it, we prefer to subtract the mean divided by the standard deviation. But however you rescale, it's better to rescale in a way that I disagree with than to not rescale at all. Put it on 0, 1 is fine. Now, fitting the weights is going to be an iterative process. One thing to be mindful of is that if it takes a long time to converge, that's a sign that you have a poor model data combination. Now, long time to converge also could just be the fact that if I have a lot of parameters, a complicated model, it's going to take longer for it to converge. So just, so as you work through your projects, if I've got a lot of data, a lot of parameters, and it takes a long time to converge, it takes a lot of iteration, well, that's a sign that I don't have a good combination. But so it could just be the data size, it could be it could be the complexity of the model, or it could be it's a bad fit. We don't really know why it's going to take a long time. But it's just something to kind of ping in your mind. I haven't seen that written down anywhere, that if it takes a lot of iterations to converge, it's probably not a good fit. but that's just something I've seen specifically with Bayesian models, and I believe it holds true everywhere else. Now, back propagation is how we actually fit things with gradient descent. We're going to input a data set sample into the neural network. We're going to compute the output of the network. We're going to do a forward pass. So what's happening here is that the system kind of just comes up with just, with values for the initial coefficients, the initial weights, and it just runs through. Now it's going to actually compare the predicted values to the actual target variables to calculate the error, and it's going to propagate backwards to improve those weights, to improve those coefficients to get a better accuracy. And it's going to adjust the weights to minimize the error. So what happens is Python is going to just throw in some coefficients. Either it'll have like preset values or it'll do random. There's a bunch of different ways that it goes about it. If there's another model that is similar, that looks like it has, it's related to your project, maybe a new data set, you can start out with those coefficients as the initial values, and it takes those values, runs through that whole process from left to right of sending the predictors through. Then it takes a look at the error, and then it adjusts the last hidden layers coefficients to improve the model, and then it moves backwards to improve the coefficients. It moves backwards to move the coefficients. Keep on doing that. Then it repeats this process over and over and over until it gets the best model it can. And so this is a gradient descent approach, is how it actually decides what the adjustment will be. All right, now we are super prone to overfitting with neural networks because they're so flexible, because they're so powerful. It's a double-edged sword. My personal rule of thumb is that I want 30 training observations per parameter. That's just how I like to go. I think that's a little bit high, honestly, but I've never been burned by this rule. Now, the parameters that we need to consider. I'm going over scikit-learn right now for MLP classifier and MLP regressor. These are just, frankly, I feel like it's just like the simplest neural networks to build. And the two that are going to be the most important to deal with are going to be the hidden layer sizes. So the number of hidden layers I have, number of nodes in each layer, and then the activation function are the two that I put the most emphasis on. All right, so the default is to have one layer with 100 nodes. If I did 100 comma 50, I'm going to have two layers. First one has 100, second one has 50. However I set this up, whatever this tuple is, determines the number of nodes in each layer. Now, for the activation function, we have the identity, which means that I'm taking straight values. This is going to be similar to like multiple linear regression for my generalized linear models. I could do logistic for the sigmoid curve. I use hyperbolic tangents or ReLU. ReLU is the default. And what this does is that this does a piecewise defined constant function and then a slope. And there's all these others that we can mess with. Don't know, leave the defaults as is. Now, scikit-learn's version, that it'll take the training data and automatically pick up a validation set for me. So in this video, I'm not going to have a validation data set. The default is to take 10% of your I just have 10% of your training data put in there. All right, so I'm going to use the heart disease data set once again. I'm going to go through and do my data prep. I've got categorical and numeric predictors. All variables are coded numerically. And so these three are coded as binary. These are coded as integers, and I need to change that over. I'm going to bend my target variable so I only have two levels, no disease or disease. I'm going to fill in the missing values with the mode of the column. And for my split, I'm going to do 70 training, 30 tests. And I'm not going to manually set a validation set because I know 10% is going to get randomly assigned to it. I'm going to use dummy variables to get my categorical data, my non-binary categorical data prepared. And then, I'm just going to go through and, so I need to do transformations. Remember, neural networks suffer all the problems of generalized linear models. So I'm going to go ahead and use Yo Johnson to do a power transformation on my numeric data. Doing that here. And then I'm going to go ahead and standardize by subtracting the mean divided by the standard deviation so that my prepared data has a mean of 0, standard deviation of 1. And now I'm going to go through and just do a grid search. All right, so something I find for parameters, if I want a full range, the default is 100. So if I only could do 3, I would do 50, 100, 200, half, default, and then double. Well, if I wanted a little bit more of a grid, a spread that I find works out very well is use a Fibonacci number. So I'm just going to use some Fibonacci numbers. Honestly, a hidden layer of with just one node really isn't much to call home about. So I've got a minimum of 2. And we're going to do identity. So this corresponds to multiple linear regression. Logistic corresponds to logistic regression. Hyperbolic tangent, well, it's using hyperbolic tangent, which we could use in generalized linear models, but generally we don't. And then ReLU, which is the default, the classic one. All right, so I'm going to create a data frame where in the first column, I have the number of hidden layers. Second column, I have the activation function. I have the fitted model. And then I'm going to store my train and test statistics in these columns. Validation, to be consistent with my other videos, I put it here, but I don't have a validation set held out. And so when I do my train statistic, that's going to include my training data and my validation data in it. And so I'm going to predict the probability on each of these. Let's go ahead and get the AUC off of each model. And I'm going to sort by the values I get, test and train. All right, so now look at this. Look at the test values, 0.78, scrolling down to 0.83. That's really not a wide range. So as I look through this, there isn't a whole lot of distinction between my models. Now for training, it looks like I do have a little bit of overfitting as I look through. Look at this. I've got 0.9 and 0.81. There's a little bit of a gap in that. So this model looks like it's overfitting on me. And so I would be concerned about overfitting in this situation. Here's 0.92 and 0.8. So I've got some overfitting that I need to be worried about with this model. Now, if I go through and plot the test statistics, look at this. It's pretty flat. Now, so remember, I'm doing a spreadsheet problem. Now, it would be a lot more complicated. This is, just a short YouTube video. I'm not going through the whole process of what I would go through if I was doing a full project for like, computer vision or something like that. But this is a good place to start. Spreadsheet problems is a good place to just learn, the vocabulary and work on things just because it's a little bit more concrete to us. Notice that I'm not getting a whole lot of bang for my buck by increasing the number of nodes. And the reason for that is, well, it's a spreadsheet problem with not a lot of observations. The small data set enabled me to quickly do the computation, so I didn't have to sit and wait all day to be able to film this video. But there's, you can see that I really didn't get a whole lot more by fussing with more nodes. All right, so neural networks, super powerful in the right context, not super powerful here. That's just how machine learning works out. You try a lot of models and a lot of them end up being thrown in the bin. But they've got power, they've got utility. They are prone to overfitting, and they suffer every problem that generalized linear models suffer. We have to do more data prep, but it's a double-edged sword. Super powerful, but you can cut yourself with that blade. Well, that's all I've got for you. Life is short. Do math.